Here's a plane through the origin in R3. This is a subspace, and here's a line through the origin, also a subspace. Their union contains every vector that lives in one or the other. Most students expect this union to be a subspace too, but watch what happens. Take a vector v equals 1, 0, 0 from the plane. Now take a vector w equals 0, 0, 1 from the line. Add them together using the parallelogram rule. The sum is 1, 0, 1, but this vector has a non-zero first component, so it's not on the line, and it has a non-zero third component, so it's not in the plane either. The sum lands in neither the plane nor the line, so the union is not closed under addition, which means it fails to be a subspace. Intuition can fail you here. Let's build the rules. To answer that, we need to define subspaces. Let's start with the bigger concept, a vector space. A vector space is a collection of vectors where you can add any two vectors together and multiply any vector by a scalar, and the result always stays in the collection. You never leave the set. R2, the set of all pairs of real numbers, is a vector space. R3, the set of all triples of real numbers, is a vector space. Even the set of all continuous functions on an interval forms a vector space. For the rest of this video, R3 is our ambient space. The space we'll be working inside. A subspace is a vector space living inside a larger one. It must satisfy two rules. Rule 1, closure under addition. If v and w are in S, then v plus w must also be in S. Closure means the result stays in the set. Rule 2, closure under scalar multiplication. If v is in S, then c times v must be in S for every real number c. These two rules actually collapse into one unified condition. S must be closed under all linear combinations, expressions like c times y plus d times w, where c and d are real scalars. Let's do a quick check in R2 and let S be the x-axis, meaning all vectors of the form x, 0. Take v equals 3, 0 and w equals -1, 0. V plus w equals 2, 0. That's still in S. 5 times y equals 15, 0. Also in S. Both rules pass. Rule 2 has a powerful consequence. Suppose v is any vector in a subspace S. By rule 2, c times v must also be in S for every scalar c. Now set the scalar c equal to 0. 0 times any vector v gives the 0 vector. So the 0 vector must belong to S. This means every subspace must contain the 0 vector. This gives us a fast first test. If a set doesn't contain the 0 vector, it cannot be a subspace. Here's an example. Look at the plane. Z equals 1 in 3-dimensional space. This plane floats above the origin. The 0 vector, which is the point 0, 0, 0, has z equal to 0, not 1. So the 0 vector is not in this set, and therefore the plane z equals 1 is not a subspace. Here is the complete catalog of subspaces. In R3, there are exactly 4 types. First, just the 0 vector alone, a single point sitting at the origin. This is the trivial subspace, and it has dimension 0. Second, any line through the origin. Think of the x-axis or any line that passes through 0. This has dimension 1. Third, any plane through the origin, like the xy plane is the classic example. This has dimension 2. Fourth, all of R3 itself. This has dimension 3. And that is every possibility. Dimensions 0, 1, 2, and 3. Every subspace of R3 fits into exactly one of these 4 categories, and every single one of them passes through the origin. Now that we know the rules, let's stress test them with a concrete example. Let P be the xy plane in R3, and let L be the z-axis. P is a subspace. It's a plane through the origin. L is also a subspace. It's a line through the origin. Now consider the union, P union L. This is the set of every vector that lies either in the xy plane or on the z-axis. Pick v equals 1, 0, 0 from P. Its z component is 0, so it lies flat in the xy plane. Pick w equals 0, 0, 1 from L. Only the z component is non-zero, so it lies along the z-axis. Now add them. V plus w equals 1, 0, 1. Is this sum in P? The z component is 1, not 0, so it does not lie in the xy plane, not in P. Is it in L? The x component is 1, not 0, so it does not lie on the z-axis, not in L. The sum belongs to neither subspace. It floats in empty space outside the union, therefore P union L is not closed under addition, and so it is not a subspace. This demonstrates that the union of two subspaces generally fails to be a subspace. Unions fail, but intersections always work. The intersection of two subspaces is always a subspace. Here's the proof. Let S and T be subspaces and take vectors V and W in S intersect T. Since both V and W are in S and S is a subspace, V plus W is in S. Since both V and W are in T and the T is a subspace, V plus W is in T, so V plus W is in S intersect T. The same logic applies for scalar multiplication. If C is any scalar, then C times V is in S because S is a subspace, and C times V is in T because T is a subspace, so C times V is in S intersect T. Closure holds, so S intersect T is a subspace. Let's look at two examples. First, intersect the xy plane with the z-axis. The xy plane consists of vectors of the form a, b, 0, while the z-axis consists of vectors of the form 0, 0, c. The only vector in both has all components 0, the 0 vector. That's a valid subspace. Now intersect the xy plane with the x-axis. The x-axis consists of vectors of the form a, 0, 0, which all lie in the xy plane. So the intersection is the entire x-axis, though also a valid subspace. Here's the bottom line. First, test a subspace by checking closure under addition and a scalar multiplication. In other words, closure under all linear combinations. Second, every subspace must contain the 0 vector. No origin, no subspace. Third, intersections of subspaces are always subspaces, but unions generally are not. Fourth, the complete list of subspaces of R3 consists of just the 0 vector, lines through the origin, planes through the origin, and all of R3 itself. These ideas underpin column spaces, null spaces, and the 4 fundamental subspaces of a matrix. Every time you encounter a new subset in linear algebra, the very first thing to check is whether it's a subspace.